Hi everyone. In this video we are going to talk about acceptance rejection algorithm for continuous random variables. So I am going to use the short form AR for acceptance rejection algorithm. I will do the work on the continuous version, and the proof for the discrete version is very similar. For continuous random variables, R.V is my short form for random variables. So the first step is we generate a random variable y that is coming from G, distribution gy, right? Or you could, this is just the short form for g of y. Then what you do is you generate a u, a uniform u, independent of y. Now, if u is less than equal to f of y over c times g of y, sorry, this should be lowercase. Whatever you have realized, that's what you put in here. So for when you generate from this y, it's like some y equal to y, say. Because what we are trying to do is we are trying to generate from y, gy, and we are trying to generate an x. Sorry, this is an x. If this is true, so if u is less than equal to this ratio fx evaluated at the y that you have generated divided by c times g of y evaluated at y, the y that you have generated, then you set x equal to y. Okay, I'm sorry, this is a little y, should be smaller. X equal to y. That is basically you accept. Otherwise you go back to 1. So before we prove this, and there are several things that are noteworthy here. First of all, fx y and gy y. So this is the PDF from which you want to generate f of x. You want to generate a random variable x, but you generate a random variable y coming from gy, and then you do some tests to make sure if you can keep that y as your x. So these are random variables, and therefore the ratio f x evaluated at y over, sorry, this would be the uppercase y, gx evaluated at some y, this ratio, this is the y, this ratio is independent, is a random way, is independent of u in step 2. Also, this ratio is bound by bounded between 0 and 1. So this ratio is always going to be between C times G y of y is always bounded between 0 and 1. Sorry. So let's turn to the next slide. The number of times n that steps 1 and 2 need to be called basically the number of iterations which are needed to successfully generate x is itself a random variable. And has, yes, you guessed it right, some of you probably have already guessed it, that it has a geometric distribution. Because you're counting the number of failures before you get the first success, right? With success probability, P equal to probability that you would be successful only when u is less than equal to f x evaluated at the y over c times g y y. So if you had to write the PMF, P of n equal to n is 1 minus little p to the power n minus 1 failures before you achieve the nth success, n greater than equal to 1. Thus on an average, the number of iterations required is given by expected value of this uppercase n, or the geometric random variable n, and we all know that expected value of the geometric random variable n is 1 over p, where p is the success probability. So in the end, basically, let's switch the slide. In the end, we obtain our x as having the conditional distribution of y. So it has having the conditional distribution of a y given u is less than equal to f x y over c g y y. So if you do a direct calculation, it's going to lead to, you can do some calculations and you will get P is equal to 1 over C. So probability that U is less than equal to fxy over c gy y, given that y is equal to y, is f of y fx of y over c g y, because u is uniform, right? So u less than equal to this, given y equal to y, is simply fx evaluated at y over c gy at y. This unconditioning and recalling that y has density, remember that y has density gy, so recall just erase this part. You recall that y follows gy. So P is equal to the integral f of y fx evaluated at y over c gy dy, negative infinity to positive infinity. What are you going to get if you evaluate that? So you can take 1 over c out. Fy dy, which is equal to just 1 over c, because this is a density function, so the integral of over the entire support set for density function is 1. So therefore expected value of n, which is 1 over p, and p is 1 over c, so this is equal to c. Oops, sorry, I forgot the gy here. This times gy dy. So once again, we obtain our x as having the conditional distribution of y given u is less than equal to fx over c gy. Now p is equal to 1 over c, so probability u less than equal to fx over c gy given y equal to y is nothing but just fxy over c gy, because its u is uniform. So this part here, this equality holds because u is uniform. Also recall that y follows gy, so p is negative infinity to positive infinity. This conditional probability, which is fxy c gy, and you integrate it with respect to, so you integrate it with respect to y and for the curve gy. So what you get is 1 over c. and these two cancel out, so it's 1 over c f of y dy, and because this is a density function, so this integral, hence by definition it integrates to 1 because this is a density function. So it integrates to 1. So we get this, the p is equal to 1 over c. Now we know that expected value of n is 1 over p because n is geometric. So since p is 1 over c, so 1 over p is c. So expected number of iterations required on an average is c. This expected number of iterations of the algorithm required until an x is successfully generated is exactly the bounding constant also. So it is also the bounding constant. So this expected value of n equal to c is also called bounding constant. And we can now indeed see that it is desirable to choose our alternate density g so as to minimize this constant. So you want to pick g y such that it minimizes c. So basically c is supremum of x fx, this ratio fx over gx. Remember, f is the density for curve for x and g is the density for y, it represents the density for y. So that's how you pick the c. So in short, it's I mean, the optimal function would be gx equal to fx, right? That would give you the optimal function, which is not what you have in mind because you want a gx which is from which it is much easier to calculate to generate the random variables. So in short, it's a bit of an art to find this appropriate g. At your level, it's going to be pretty easy and obvious, like you will have like some choices which would be very obvious. So I will stop this video here. In the next video I will continue the proof that this algorithm works, which was the main reason for this series of videos.